24, 25, 25, 26, 27, 28, 29, 30. Classics number 1, 2, 3, 5, 5, 6, 6, 7, 8, 10, 11, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 23, 24, 26, 27, 28, 29, 30, 3, 21, 6, 15. Sorry? 5 to 5. Huh? Okay. If I ask you to scan the code, please do not look for someone else who is not in the class, because I can detect it. Okay? This time, students who have done it, they are not going to be punished, but next time, do not do it. If you scan 2 times and you log in for someone else who is not in the class, I can detect that you use the same device twice. Clear? Clear? Do not do it again. I have found it in my record. Just to let you know, if I display the QR code, do it only for you. Do not do it for someone else who is not in the class, or for your friend who is even in the class. Because if you use the same device, I can detect it. Clear? Don't say you are not aware about it. Now, we're going to continue with the direct map caching technique. Please, everybody, pay attention to this, because I'm going to ask you to solve this as well. Now, for direct map caching, to find the cache line, we take the block address from the main memory, mod the number of cache lines. Now, here we have 8 cache lines. We have to find the block. Then we have to find the cache line for each block. Now we have the different blocks, that is the decimal addresses of the reference. We have 22, 26, 22, and we have 26, and so on and so forth. So we do, please make sure you do follow me. We have our block number 22 from the main memory. Since we have 8 cache line, we do 22 mod 8 is 22 mod 8 is 22 mod 8 is 6. So that means block number 22 from the main memory will be loaded into cache line 6. So we have 6 here. Right? 6, and this is the block, has to be here, 22. This is the cache line, 6, then we have our block 22 here. And because 22 is the first time to be loaded into the cache line, this is a miss. Because it's the first time to load these blocks into the cache line. Now, block number 26 from the main memory. Class number 5, number 26, get ready. 22 Mod 8 is 6 and is a miss because it's the first time to load this block into our cache. So we put this block in line number 6, cache line number 6. Now 26, block number 26 from the main memory will be loaded into which cache line? Since we have 8 cache line, class 5 number 26. Which cache line? Our block 26 needs to be loaded into cache. Huh? 26 mod 8 is 2, right? Everybody. 2? Yes. 26 mod 8 is 2. So we have 2 here. The block number 26 from the main memory will be loaded into cache line 2. And it is a miss because it's the first time to load this block into the cache. So we have block 26 here. Now 22 will be loaded in which cache line? 22 plus 6 number 22. Block number 22 will be loaded in which cache line? Class 6. 2. 22. Block number 22 from the main memory will be loaded in which cache line? We have 8 cache lines. That is 22 mod 8 is 6. So that is a hit because we already have block number 22 in cache line 6. So this is a hit. Is already here. Now the next one is 26. Block number 26 will be loaded in which cache line? Class 6 number 26. Class 6 number 26. Absent? Absent. Class 6 number 26. The block number 26 from the main memory will be loaded in which cache line? We have 8 cache lines. That's 26 mod 8. Mod 8 is, we have the answer already there. 26 mod 8 is huh? 2. So we have 26 to be block to be loaded in cache line 2, and since we have already 26 in cache line 2, this is a hit. We have a hit. Next one is block number 16. Number 16. Class 5. 16 mod 8 is number 16. Class 5. Class 5. 0. In cache line 0, and this is a miss. Next is block number 3. We reload in which cache line? Block number 3. multiplied by 8, what is the remainder? Class 5, number 3. What is the block? What is the cache line for this block number 3? 3. So we have 3. And since it is the first time to load this block into the cache line, it is we have block number 3. We have 16. 16 we have found the cache line, mode 8, that is 0. And 16 already in cache line 0, that is A, that is a miss, is a hit. We have a hit here because we already have the 16 block in. Next block is 18, number 18, plus 5, 18. Class 5, number 18. The block number 18 will be loaded in which cache line? 2. Good, because this is the first time to load this block into the cache line. And we have to load the block number 18. Now we have the last one. The last one is block 16. 16 will be loaded in which cache line? Cache line, and it is a hit because it's not time already in block. Now, we found easily the hit length. Also found the methylation equal to the total number of misses divided by the total number of. How many hits do we have? We have how many hits? 1, 2, 4 hits. And how many sequences do we have? 2, 3, 4, 5, 6, 7, 8, 9. We have 9. Then how many misses do we have? So let's divide by 9. We have 0. 5, 5. Hit relation as well as the miss relation. Continue with cache. We have the line of the cache, and we have V, that is the valid bit to indicate if the data is valid or not, and we have the tag to indicate the address for each cache line. We have the data corresponding to each cache line. So this is the initial state of the cache after it is powered on. that means the cache is empty, and we have all valid bits that is set to not indicate that this data is not valid. That means the line is empty. So the next one, we have to load this data 10110. That means the upper 2 bits, they are there to indicate the tag, and the 110, it is there to indicate the index. So we have 110, then we set the valid bit to yes, because now this data is valid. Then we have 10 for tag, and this is the data at this memory location. So this is how it does. The next one, we need to handle the miss of 1101. We have 101 to indicate the index, to indicate the line. We have 100. This is the line. We need to set the valid bit to yes. Then we load the tag. That is 11. The next one, we have to handle a miss of the address 100 and 00. So we have 000 as the index. This is the line. We need to set the valid bit to yes. Then this is the tag 10, and we have the memory address of the data that we need at this line. Clear? Is this make sense to everybody? Hello? Is this make sense to everybody? So the upper 2 bit is for tag, and the lower 3 bit is for index. And we needed to set the valid bit to yes once we have loaded the data into the cache line. So we have also to handle this miss. The upper 2 bit is for the tag, and the lower 3 bit is for the line. That is 011. So 011 is here. We needed to set the valid bit to yes. Then we have 00 here, as it is for the tag address. The next one, we have 100 and 10. We have the cache line, the cache index, which is 010. We have 010, and we need to set the valid bit to yes. Then we include the 2 bits for the tag. Then we can load the data into the specific cache line. Clear? Now we have the mislate versus the block size. Here we understand that the mislate goes out here if the mislate goes up if the block is too larger relatively to the cache size. That means that each line here represents a cache of different size. So this figure is independent of the set associated that we're gonna learn later on in this class. So we have the block size, and here we have the cache size. So as the block size goes up, you see that the mislate also goes up. We see here we have 128 block size, and here the cache size is 256. You see that we have a normal mislate. But as the block size go up, for example, you see here we have 16 cache size, and the block size here is 128. That means we have a mislate which has to go up. And here we have 16 for the cache size, and the block size is 64. You see that the mislate has gone up. We have here 32, and here we have 16. It has also to go up, as you can see. But this feature is independent of the set associated that we're gonna learn. So we have to measure and improve the cache performance. That means we have to calculate the CPU time, which is has to be divided into parts. We have the CPU execution time, and also we need to evaluate the memory start time. So the CPU execution cycle is the time that the CPU spends actually learning instruction. It does also include the cache hits. memory star cycles. This is the time spent waiting for the memory cache, including the memory misses. Cache misses as well. So the overall CPU time is equal to the execution cycles plus the memory stalls cycles times the clock cycle time. Now the next cache mapping technique that we're gonna learn today is the fully associative. The fully associative. A memory block can be placed in any cache location. At any memory block can be mapped in any cache location. That means there is no fixed cache mapping that must be checked. So must check all cache entries to find a block which is armed. It has to use parallel comparator. So one per entry. However, these techniques have to use many comparators, which increase the complexity of the system, and also as a result, it does increase the cost. It is suitable for small caches due to its high cost. So the second one is fully associative. That means block line, a block line, memory block line can go to any cache line. We have main memory block, which needs to be loaded to any cache line. The third one is set associative. Three is set associative cache. For set associative, this is a middle approach between the direct map and the fully associative. That means a block from the main memory needs to map to a specific set uses the index. A block can be placed in any position within that set. N-way set associative has n block per set. That means the cache is divided into multiple sets and each containing n blocks. On access, only the block in the selected set are set. So combining the direct map, that is one set, and a associative search within the set. Now, in set associative, we have to find the cache line. Cache line equals to the block address mod number of sets. Now, this is a one-way set associative. Block number. That should be block number to make it clear. Block number or block address. Block number mod the number of sets in the cache. So we have one-way associative. That is the direct map. We have 8 cache lines. Then two-way associative. You see we have two way in each set. The set number 0 we have two-way. This is one way 1 tag data, tag data. Tag data, tag data. So we have two ways. Here we have one-way set associative. That means we have the direct map, and this is a two-way set associative. You see we have two ways, tag data, tag data. Then we have four-way associative. That means we have 4 ways. Here we have tag data, tag data, tag data. We have 4 ways in each set. So we have also a 8 set associative. So this is just the direct maps, and this is two-way set associative, and this is four-way set associative, and this is eight-way set associative. Now we have a block placement comparison in different cache organizations. For the direct map, we have the location of the block number 12, who is needed to be loaded in the cache line number 4. Now, pay attention. Here we have block number 12. Block number 12 from the main memory. Block 12 from the main memory. Using a direct map, we have 8 cache lines. During the direct maps, we have 12 mod 8, then we found the cache line 4. That means the block number 12 from the main memory needs to be loaded in line 4 in the cache memory. Okay? That is 12 mod 8. For two-way associative, so we have here 4 sets. Now we need to do 12 mod 4. That is what 12 mod 4 is. 12 mod 4. Huh? 12 mod 4. Here we have 4 sets. This is the number of sets. 1, 2, 3, 4. We have 4 sets. Now we need to load the block number 12 from the main memory. In which set the block needs to be loaded into. We do the block number mod the total number of sets in the cache. 12 mod 4 is 12 mod 4. Huh? 12 mod 4. 12 divided by 4. What is the remainder? 0. 12 divided by 4. We have the remainder. So that means using four-way associative, our block associative, our block number 12 will be loaded into set 0. That means we have here this block number 12 doesn't need to be loaded in any way of this set 0. We have this block to be here or to be here. Okay. So we have fully associative. For fully associative, we have 8 lines, and the block can be line. For fully associative, we have main memory block, which needed to be loaded into any cache line. That means we can have line up. The block 12 line. So this is just a block placement comparison in direct cache mapping, 4 set way associative and the fully associative. Question? 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 Now we have a simple exercise here on the screen. We have to assume that we have 3 three small caches, and each containing a 1-word block. That means we have 4 cache lines, and one cache is fully associative. The second one is two-way associative. That means we have two-way associative, and we have the third one, which is a third direct map. We need to find the number of misses for each cache organization given the following block sequence. So we need we have block 0, block 8, we have block 0, and we have block 6. We have block 6, we have block 8, we have block 0, we have block 6, we have block 8. How many cache lines do we have? This is for direct map technique. How many cache lines do we have? Do we have 4 cache lines? Zero mode 4 is number 8. Zero mod 4 is 0. 8 mod 4 is 0. 6 is number 6. Number 6. 6 mod 4 is number 6 plus 5 plus 6. 0 mod is 2. 8 is, so this is 0, this is 0, this is 2, this is clear. So our block number 0 cache line 0. So that means this is also a mean, and also a mean equals 8. Also a mean. Also is a mean. This is also a mean because the block. So we have 5 means for the caching. Now to found the set for each block, we have block 0 which need to be in set 0, and we have block 6 which need also to be in set 0, and we have 8 block which need to be in set 0. So we also need to found the misses and the hits. Now we have 4 sets. We have here we have the block number 0 from the main memory, which needs to be loaded in set 0. And we have the block number 8, which also needs to be loaded in set 0. Because we have two-way associative, is fine. Now we have the block 0, which needs to be loaded into the set number, the set 0, and it is a hit because we have already found, we have already loaded this block into the set 0. Now we have 6, which needs to be loaded into the cache line, into the set line 0. So it has to replace one of the previous blocks, and we needed to use a replacement technique. So in this case, we're going to use recently used. We're going to discuss about these block replacement techniques. So that means we're going to replace the least recently used. In this case, it is 8. Now we have block 8 that needs to be loaded into the set 0. Then we have block 0 and 6. Then we need to replace the block 0 because it's the one which is recently used. So this way we have 4 misses for the set associative technique. Clear? Hello? Clear? Is this clear? Huh? So for fully associative, we have all the blocks that need to be loaded into the cache line. Since we have how many cache lines? We have 4 cache lines. So we have the block 0 that needs to be loaded in the cache line 0, and we have the block 8 that needs to be loaded in block 1 because we can put in any cache line. We have 0 that is already loaded, this is CD, and we have block 6 that can be loaded in block 2, and we have the block 8 that can be loaded in block 1 because it's already there. So that means here we have flexibility for this type of cache mapping that is fully associative. Now you see it has typically achieved the best performance in this example because we only have 3 misses. For fully associative we have 3 misses, and for set associative we have 4 misses, and for direct map we have 5 misses. That means we have the fully associative which has a best performance. Is this clear? Question? Questions? What? No question. Question? Questions? How many minutes left? 5? Questions? Questions? Now, we just learned about these mapping techniques. For direct map, we have to find a specific cache line for a specific memory block. By this expression, we have to find the cache line for direct map. We have cache line equals to the block number mod number of cache lines. Cache lines. For set associative, we have the cache line equals to the number of block number more the number of set block number more the number of set. Here it is. We have the block number more the number of set in the cache line. Then we have the fully associative. The cache line. A main memory block can be loaded to any cache line. Main block, memory block in any cache line. We have found that for the fully associative, it does reduce the number of misses. That means it has a best performance because it does use many comparators. That means that it is very expensive because it does include many comparators and the system needs to be more complex. That means this system, this technique of mapping can achieve best performance, but it is very hard to implement it since it does include many comparators, and as a result, it does also require high cost. So these are the mapping techniques that we just learned for the cache. In today's class, we learned about cache memory. We have learned why we have the cache memory in our computer system. And since the cache memory is smaller than the main memory, that means not all main memory blocks can be loaded into the cache lines at the same time. We needed to learn some cache memory mapping techniques to allow the system to load a specific main memory block into a specific cache line. If no question, that's it for today's class. All right, that's it for today's class.